So let's take a look here. We are on chapter 13, which is on page 117. Stream route cruising here. And I'm going to get this light on real quick. Take a look at the top of page 117. Okay. So first, I want to talk about near Earth gravitation because you're already an expert at that. Let's say this is the ground. I have a box right here. What's the force due to gravity that acts on this box? mg, and it acts at the box center mass, right? So we know that it's mg and that the direction is towards the center of the Earth. Technically, most of you probably would say it acts downwards, right? Well, what if you're on the opposite side of the planet? Downwards would be, right? Towards the center is the most general way. So
kind of like how centripetal forces.
exactly, right? Because if you think about the entire planet, let me just bring it in here. I'm just trying to point out that if you're at different points on the Earth's surface, right, the downwards direction might be in a different direction. You know what I'm saying? So towards the center would be a more general way to describe it. Is that good? Yep, yep. Okay. It turns out we can generalize this when we're not near the Earth. And so we're going to call that universal gravitation. You can take any two objects. Let me try and do it the same. Let's say this is object 1. And this is object 2. It could be a spaceship and an astronaut. It could be a planet and a moon. It could be the sun and the Earth. Any two objects. It could be an apple and your head, right? Any two objects. And I want to try and use this notation. And it may not be exactly the same notation as you see everywhere else, but it's analogous. So, and I'm going to try and be consistent with this notation. First, I want to describe a vector that goes from the center of 1 to the center of 2. All right? And I'm going to call that R1 to 2. Sometimes I get lazy and I just say R12. Okay? This is notation I'm going to use in this class and in circuits class. Okay? Now, there's a unit vector that points the same way. Notice this would be R hat. It's a unit vector. Or sometimes we'll say R hat 1, 2. Okay, so we're going from 1 to 2. All right. Obviously, this is going to have some mass, M1. Maybe I'll make the 1 in blue. Maybe I'll make the 2 in green. And there's some mass up here, M2. Let's do it that way. And I want to talk about the force. Whoops. The force that 1 exerts on 2. Sometimes I'll call that F1 on 2. I'm going to underline that word on. And so for me, I'll write it at F1, 2. Those are the different ways. At the beginning, you should probably include the words to and on. So when you're first learning this stuff, you should probably include that word to. It clarifies your work immensely for a new student. Well, or at least some. Okay, so now, what does this relate to? Let's make sure I don't screw this up. There's going to be a constant. I'll explain that constant in a minute. This is called big G, not little g, big G. Okay? What factors do you think affect the gravitational force between two bodies? The masses and the distances. So let's get that involved. We're going to expect both masses would have an effect. And the distance between them. And it turns out it's proportional to that distance squared. So now let's see how I want to write this in this case. Notice something special here. This is not a vector right now. This is a distance. In this chapter, one of the key things you have to pay attention to is whether or not something is a vector or a scalar. That's just all the time, every single problem, always pay attention. R1 to 2 is center to center distance, not displacement vector. Distance. So that's just the distance between them, not the vector between them. The direction is negative R1 to 2 hat. A hat vector describes direction in 3D. So far, so good? It turns out a very common way to rewrite this is to get rid of the hat vector using this trick. R1 to 2 hat is equal to R1 to 2, whoops, see, I'm already leaving out that word. So the definition of a hat vector is the full vector divided by the magnitude. Notice when we plug that in, it looks like an inverse cube law, but it's not. It's just easier to code. What? Oh, never mind. Give me just a second. So if you use the hat vector, which is the mathematical standard way of describing a direction, we get a hat vector over r squared, and there should be a minus sign. I forgot a minus sign. I'm going to put that in up here. However, in practice, rather than taking the time and effort to do this extra step, what we oftentimes do is just say you take the full vector and divide it by r cubed, because one of them gets the r hat. And again, notice that minus sign right there and right there. It's equivalent. There is the minus sign. So far, so good? Yes, question.
Could we just like say r? It's like it's a distance, so it's like it doesn't have to be 1 to 2.
Yeah, you could. But in my experience, I like to describe this thing. So what he's saying is, could I just use r squared here? Absolutely. But what if you're coding this like you're going to be doing tomorrow in lab, and you have 3 of them? Pretty soon it gets hard to keep track because you got 1 to 2, 2 to 3. And so it's easier in the long run to just get used to keeping track of each separate Does that make sense?
Yeah.
You don't need it for 2, but for 3 or more, which is more standard, and that's gonna be your final exam question, so let's get used to it. Good? Yeah, usually I put a 3-mass system on your final. All right. So I will point out one last thing here. Notice the magnitude. If I want the magnitude, I just ignore this direction, right? That would be G that's the magnitude. And notice everything in there is positive. Now I know I said I would explain the constant. Big G, that's what everybody calls it. We call this one little g, and we call this one big G. It's 6.67 times 10 to the negative 11. Gravitational forces are extremely small for most real life masses. For example, I'm a mass. Each one of you is a mass. I'm attracting each one of you with a gravitational force. But when you take our masses, which are about 100 kilograms, so let's say we have 100 times 100 times 10 to the minus 11, that force is negligible. That's why you aren't suddenly drifting towards me. Okay, all right. Let's get the units on this freaking constant. Help me out. Look at this equation right here and help me get the units for G. It's got to be, what are the units of this? Newtons, cross multiply. We know it's got to be newtons times something divided by something. Newtons times meters squared over kilograms squared. Yes. So if you're wondering what that constant is, there it is. Cool? All right. So in practice, what are we going to do? We're going to put some masses somewhere, figure out the R vector, plug in something, solve for something. And then we can do problems with universal gravitation. So far, so good? Well, we've talked about force. What's another concept we've talked about this semester that's been pretty useful? Energy. So let's talk about gravitational energy in this new regime. Okay. So here, let's do it on the other board. Near Earth, we would sometimes have a box, something somewhere up in the air. We would pick a reference level. We'd call this height H. And we'd say U due to MGH, whatever. Let's just say it like that. Right? You remember that? So that was near Earth. And the units popped out as joules. All right. I'm gonna actually partially derive this to give you an idea where this comes from and then write the answer, right? Because what we're gonna do most of the time is use the answer, and I can go into the derivation more later. But remember, delta U is minus the work done. Do you remember that from earlier in the semester? Right? Does anybody remember what the integral form of work was? The integral of what? Force dot displacement. Yes, excellent. Now, I want to point out, in this case, the force is in the radial direction. So I'm going to write that over here. we had G and then I need to dot that with some sort of radial vector. Now here, maybe I should be using 1 to 2. Now again, I'm not going to expect you to do this derivation, but just hear me out. You see there's a minus sign here, and there's a minus sign here, and they're going to cancel, right? But then, do you agree when you integrate this, if we have an R 1 to 2 here, I'm going to get another minus sign because this is a negative power. Do you agree? So there's 3 minus signs, and that's just what I wanted to point out. You might think, and then remember there's a delta U. So there's a final minus initial, and there's other stuff. We could do this derivation later. But in the end, when you integrate, this is going to go to a first power, and it'll be negative. So that's a little bit weird. Now remember, we talked earlier in the semester about how you can think of energy as being like money in the bank. So you might say, what is negative money? Well, that's like saying you owe the bank money. We all know that, unfortunately, know that experience. So it's okay to have a negative. Now, I also said something earlier in the semester, you probably forgot. Only changes in U are physically meaningful. So it turns out, talking about the energy at one point in space, it's totally fine if it's negative. What really matters is, in a problem, we're always comparing stage 1 to stage 2, right? And seeing how the energy changes. So let me give you an example here. Let's say this is object 1, and we have object 2, all right? And let's just say this is initial state, so we'll call that B4. And then let me make this a rectangle so you don't think that's a mass labeled B4. How would I say initial state? And then we have a final state. Let's say they're farther apart. In this case, I want you to think this through with me. When they're close together in the initial state, the potential energy, is it going to be a big or a small number if you have a small denominator? It's going to be a big negative number. So let's say U is large and negative. Now they're spread apart more. What's going to happen to U? Is it still negative? And you plug in, like let's say we knew all the numbers and you plugged it in. Mass is positive, the constant's positive, the distance is positive. Are we still going to get a negative number? Yeah. Yeah. Is it still going to be large or is it going to be smaller? Smaller, right? The denominator's bigger. Now hear me out. I want you to think this through with me. Isn't this the same thing as raising mass 2 far above mass 1? I know it's moving left and right, but instead, think about the Earth. If I go away from the Earth's center, you say I raised up. Well, now I'm spreading out the centers. I raised it up, so to speak. Yes?
It'd be the same if you're standing on the equator and you jump.
Yes, exactly. Exactly. This is like standing on the equator and jumping. Absolutely. Notice what happens to delta U in this scenario. Yes, delta U is positive. So notice we have a large negative initial, a small negative. We must have added potential energy to go upwards. Even though this equation looks weird, it's totally legit. Got it? One last thing. If you do Taylor series about this and expand it and keep the first term, you get that. I can show you that later. Believe it or not, this is the Taylor series of that expanded about the radius of the Earth. I'll tell you later. It's a problem in the book. We can look at it later. Everybody cool with this? So these, you might at first think this is totally different. It's actually the same. Okay, good. Was there a question there? I forget. Okay, any other questions? Okay, so big picture. Oh, I forgot one other thing. We've got energy problems and we've got force problems. So on your test, I'm probably going to put some masses on the page and say, hey, figure out the force on this mass or figure out the energy. Now, this is something I wanted to say about the energy. When we jump up in the air near the Earth, usually we say, I gauge potential energy. But you remember, I told you, strictly speaking, that is a complete lie. The energy is stored in the gravitational field between the Earth and myself. I'm the only one that is noticeably affected when I jump up and down. But we both share that energy. Because the Earth is so massive, we don't notice it moving, right? In this scenario, which object has the gravitational potential energy? When we spread them out, which object has the gravitational potential energy? They share it in the field. Now think about this. What if these were two equal mass asteroids and you pull them apart and then let go of them? What would they do? They would come back together, right? So you have no trouble seeing that they share the energy. What's weird is the Earth is so much bigger than us. Usually we see only motion in the small masses, like satellites or people or spaceships. But when you get to things as large as the Earth and the Moon, they're both moving. But what about the Earth compared to the sun, right? So in general, you have to think of this energy as shared in the gravitational fields between the two objects. Good enough? And I think you guys got this, but I forgot to say it over here. Let's go back one more time. What direction is the force on mass 2? Due to mass 1.
Radially inwards.
What's that?
Radially inwards.
Could you, oh yeah, so from what to what? The force on 2 is directed from where to where? From 2 to 1. So the force, oh, whoops, I was doing that in red. I apologize. Let me fix that up. I drew it over there, but I forgot to draw it up here. I apologize. The force on 2, or said another way, of 1 on 2 is this way. Well, what direction is the force of 2 on 1? By what law are you using in your mind? Action reaction, Newton's third law. Let's see if this makes sense when we do Newton's third law on this. They should be the same size, but opposite direction. Well, let's say you look at this equation and flip all the 2's and 1's. The top doesn't change. The bottom doesn't change because it's the same distance. The only thing that changes is the direction. So this is consistent with Newton's third law, and that's why I like to write it this way. Cool? All right. Any questions out there on Zoom land? You good? All right. Watch the squareds, watch the minus signs. You see how there's squared in one equation, there's cubed. The energy equation had a 1 over r, so watch that. So let's take a second and let's start easy, right? Let's do 13.1. I'm going to erase the board. You get it written up. 13.1. Okay. While I erase, I'll just do that. Okay. Look at 13.1. That's the whole chapter. We're done. Usually it takes practice.
Where's that?
Yep, I'm listening.
Is that why like they say if a meteorite was to like hit Earth, blowing it up would be like a bad idea?
Say again?
Is that why like they say that if an asteroid was to like hit Earth and like
Uh-huh.
blowing it up would be bad?
Opening it up would be bad.
No, like what? Like blowing it up.
Oh, well, it turns out it's going to depend a lot on the angle of incidence. A lot of them are just going to bounce off the Earth's atmosphere. Some, if they're too small, are going to burn up on the way in. But if they're too big, we're all dead. So it doesn't matter anyways. Yeah. Now, if you could do, right? So that's the idea. You're hearing about this a lot in the news lately, right? Of trying to have an asteroid detection system so we have time to react and alter the path. Imagine if you could interact with the asteroids far from Earth and only exert the tiniest of forces. Well, over time, that tiniest amount of force might be just enough to make it graze against our atmosphere and bounce off, right? Or yeah, so that's what's going on with that stuff in the news. But I don't really know. I just hang out and do physics problems. Yeah. Yep.
Well, if the asteroid is blown up, shouldn't these smaller pieces burn up in the atmosphere? And therefore,
Hopefully, that's the idea, right? If you could shoot it and hit a direct hit, but again, you got to think about the size of these things, right? What if you hit it with a nuclear bomb, but it's as big as the moon, right? You really think one nuclear bomb is going to shatter the moon? Probably not, right? So, yeah. And what about the fragments? What if it, yeah. So, to be fair, that's not my area of expertise. But the basic idea is if you blow it into smaller chunks, hopefully the chunks are small enough, they'll burn up and not kill us all, right? As opposed to one giant chunk that doesn't completely burn up, has a huge impact and darkens the skies for 3 years. Cool?
cool.
Okay. Yep.
One more question. Yeah, I just been
Sure.
wanting to ask. So, in the case of an EMP, I know that it requires a lot of energy.
EMPs,
No, yeah, I know.
electromagnetic pulse, okay.
Yes, I know it requires a lot of energy, like as for the sun. Which my only concern is, it's supposed to stop electricity or kind of just void a certain area of
Yeah.
electricity. Wouldn't that kill the human being since the brain uses electricity to function?
So, it's a very interesting question. I got no trouble talking about it during the break.
Yeah.
The short version of when they were first exploding nuclear bombs, right? The electromagnetic pulse from the nuclear bombs would fry out all the circuitry, right? So what if you have a bunch of capacitors in there and they're very delicate and then they suddenly get a huge amount of charge, then they're shorted out, they're not going to work anymore. Then the circuit that you designed, which requires these capacitors, is no good. So yes, you could view the electricity in the brain as related to that, but it's not the same kind of equipment and it's different. That said, if you're close enough to get hit by the EMP from a nuclear bomb, there's probably other things that are going to kill you, like the radiation poisoning. And I don't know enough about radiation bombs and the radiation dose. I used to, but not anymore. I used to be an X-ray health inspector, and yeah, that used to be my deal, but not anymore. Now I just do problems with two masses and the sun here.
Like people have survived lightning strikes, which is a massive bolt of energy.
Correct. And then yet that's also killed them too, right? So there's a lot going on and there's specifics to each situation. But I want to make sure people pass the final, so I'm going to focus on 13.1. It's a good question. We can talk about it more afterwards for sure. Got it? Not trying to, yeah, I've just got to do my job basically, unfortunately. That would be much more fun to talk about. Uh-oh, we got an eclipse. You got the sun, the moon, and the earth. Clearly, this is not to scale. Is everybody cool with that?
Nope, it's not shiny.
That's right, that's right. It's only 93 feet away. Yeah, right? All right, so we've got some numbers here. I'll write all this crap up just so we got it. Mass of the Earth, 6 times what? 10 to the 24th. If you're wondering how we got the mass of the Earth, we could talk about it in a later problem. I promise I'll discuss that. $6,400 kilometers is about 4,000 miles. That's how I remember it. That's old school. About 2. Kind of interesting, just look at the numbers. Look at the mass of the sun compared to the mass of the Earth. Not quite, but almost what? A million times bigger. 10 to the 6th is a million. But the radius is was it 6.96? Oh gosh. The mass of the moon . Oh my gosh. Sorry, it just takes me a while to write all this up. You guys could try working ahead if you're waiting on me. Take some time. But for once, we got to actually plug in numbers and get a feeling for these things. I'm not trying to waste your time here. All right. I want to talk about these distances to give you a feeling for them, okay? And I feel like it's not every problem we're going to do this, but at least for one. All right, so now look at this. Let's say they're in this perfect alignment during an eclipse, something like that. All right, and then at this case, this radius right here is radius Earth, Sun. Okay, the center to center distance. My question to you is, are these radii of, whoops, I mislabeled one, didn't I? Sorry, the radius of the sun, right there. Look at these radii. The radius of the Earth is 1,000,000 meters. This is 6 million meters. And this is about 700 million meters. That's pretty big. How does it compare to this one? Tiny. Look at this. This is less than 1%. Correction. So in reality, this should be less than 1% of this blue line. And that's the big one. This one, oh my gosh, it's 10 to the -5 compared to this. So what is that? Almost 1,000,000 times smaller, right? 100,000 times smaller. So in reality, even though these objects are huge, we're going to treat them as point particles. You understand that? And that's okay because the distances involved in astronomy are so big, we can treat the Earth, the sun, and the moon as point particles. Crazy, right? Is that enough on those numbers? All right, all right. Now, in this case, so let's put a blue box around that one. And to be clear, now look at this one. looking at the size of the Earth and the Moon, it matters more, right? The radius of the Moon is only what, 100 times smaller, maybe 200 times smaller, right? Similarly, this is what, less than 100 times smaller, only like, so the scale here is maybe a little bit closer, but it's still about 100 times smaller. It turns out if you had to have really precision measurements, maybe we would have to account for the radii here. All right, more on that later. All right. Which one of these objects do you think exerts more gravitational force on the Earth? Do you think the Moon or the Sun will exert more force? Keep in mind, what's the equation for gravity?
G1 and 2 relative.
We'll get the magnitude, so I don't have to think about minus signs. The mass matters, but the radius is squared. I don't know, is it obvious which one's going to affect the Earth more? What do you think? Let's find out.
Probably the sun.
Okay, let's see. Let's see the sun on the Earth. When we punch it in, there's a constant. Whoops, I need that to be in blue. I apologize. I wanted it blue. We're getting the magnitude here. Punch it in. Take the time to do it so you don't screw it up on test day, right? Let's all do it. I'm going to do it as well. Learn how to use the EE button, right? We got to be fast on test day, so you got to know how to use your calculator. I know it's boring. Let's do it. 6.67 EE negative 11 times the sun was 1.99 EE 30. So if we get that EE button, it's less onerous, times the mass of the Earth, 5.97 EE 24. And then divide by, I'm going to put parens around it so I don't screw it up, 1.50 EE 11 squared. Okay, what did you guys get? Is that what you got? You can also check the powers of 10. 10 to the minus 11. Mass of the sun is 10 to the 30. Mass of the Earth is 10 to the 24. Radius Earth Sun is 1.5. Whoops, let's just say 10 to the. So when we square it, that's going to be 10 to the 22. So let's see. We've got 30 plus 24 minus 11 minus 22. And I get 21, which is about the right power. And I ignored all the prefactors, so that seems reasonable. Did you guys see what I was doing there to check the math? Just checking the powers of 10 and seeing if it's within an order or two. Okay, looks good. What are the units on this force? Newtons. Remember, this has units of Newton kilogram, whoops, Newton meter squared per kilogram squared. So it cancels the meters, cancels the kilograms. Let's get the force of the moon on the Earth. Okay. Ooh. I want to get the force of the sun on the Earth, so I'm going to change this. Sun on Earth. Do you agree that doesn't change the magnitude because everything's the same? Okay. Just trying to be consistent with what we were saying earlier. All right. punch it in. Make sure you get it right. $7.35. Earth. Radius Earth Moon is this one. 3.84 EE8. I got 1.98 times 10 to the 20. Newtons. Running out of space. Normally I'd include an extra digit. 1.985. Oh, that's going to look terrible. All right, so it is as you expected. The sun is exerting more force. Which one has a bigger effect on the tides, in your opinion? The what? Yeah, so what's up with that? The sun's exerting more force on us, and yet the moon has a larger effect on the tides.
Concentrated force, by the way.
What's that?
Is it a more concentrated force?
No, no. Let me ask you this. Do you agree the equation that governs this force is 1 over r squared times a bunch of constants for each of these forces, right? What does that shape look like? Let's do it over here. Hold on. I want to discuss this here. If I have a plot, if this is r, and I plot 1 over r squared, show me with your finger what that looks like. What is the value of 1 over r squared when r is very small? When r is 0, what's 1 over r squared? Infinity. Undefined, whatever. So do you agree when we get small here, it's way up here? And it's going to fall off rapidly. Obviously, when r equals 1, you hit 1. What happens to the function as I go outwards? Yeah, it goes to 0. And I want to point out, as you get very far away, how much does this force change? Does it change rapidly or slowly when you're far away? Slowly. So the issue that we face is when we're talking about the Earth and the Moon, we're somewhere in this region on the graph where the force changes dramatically from one side of the planet to the other. When we're talking about the sun, we're somewhere way over here on the graph, and it's not changing as much from one side of the Earth to the other. So it's the fact that the rate of change in the force is different. There's a lot of factors that relate to the tides as well. And I don't want to lie to you, so I'm just going to mention this. 2 things. Look at page, sorry. Look at page 125. If you look at page 125, there's 2 important things. Number 1 is trying to understand the tides is no joke. And number 2 is not on the test. Got it? If you want to learn more, we could talk about it, but since it's not on the test, I got to focus on the basics. Understood? If you want to learn more about the tides, I would go to the NOAA website, NOAA, and learn more there. It's complicated. We could discuss it more if time permits at the end of the chapter. Is everybody happy with that? I don't know what screen I'm on. So yeah. Basically, page 125 if you want to learn more. For now, we're going to focus on this. All right. All right, so we got the forces here. What if I wanted to get potential energy? Let's see what the question. So I think we did parts A and B, right? So this was A. This was B. Part C, let's practice our potential energy formula. U, Earth, Sun, it's going to be negative G, mass of the Earth, mass of the Sun, over radius Earth, Sun. Okay, let's punch it in and get a number. There's a reason for this. I'm trying to lull you into forgetting there's a trick here. Okay, you'll see. So negative 6.67 PE negative 11.
This thing RES squared or
No. So this is good observation. The force, the distance is squared. Remember the U came from that silly integral? And when you integrate, basically you got an extra minus sign and the power went up. Right? So when you integrate this, r to the negative 2, you got to raise the power and you get r to the negative 1 and a minus sign. Is that cool? Got it? Yeah, good. And that's the most common mistake on test day is people put r here and r squared there or vice versa. Really, it's got to be r squared on the force, r on the energy. Good? That's the main deal. Okay. Okay, mass of the earth, what is that? 5.97 EV24. Yeah, okay. Mass of the sun, 1.99 EV, what's it, 30? Then we got to divide by Earth, Sun. All right, I got negative 5.28 times 10 to the 33 joules. They're having more fun than we are. No, they're not. Yeah, go ahead.
Could you just have multiply the force by?
Oh, yeah, that's interesting. In this case, he's saying, wait, couldn't I just multiply this by radius? In this case, that would work. And then make sure you stick on the minus sign. So maybe we should do that really quick for the next one, right? You agree?
Yeah.
Yeah, so punch in U for Earth, Moon. Negative G, mass Earth, mass Moon, over radius Earth, Moon. What do you get for that one? In this case, he's saying, yeah, we could, as long as we remember, I'm going to make this minus sign stand out, okay? I really don't want you to forget this.
I got 10.62 times 10 to the 28.
10 to the what?
28.
Sounds about right, doesn't it? 7 point what?
622.
28?
Yeah.
Joules. Okay. All right, hopefully that's it. If not, you can check the solutions, but that's cool. Okay, now look. I've got the potential energy from the Earth and the Sun. I've got the potential energy from the Earth and the Moon. If I add those up, do I get the potential energy of the Earth? No, that sentence makes absolutely no sense at all. Okay, remember, the Earth doesn't have the potential energy. Which objects have the potential energy? All of them share it, and so there's 3 of them. Which one have we not accounted for in the potential energy? Which pair? Yeah, so we also have to incorporate the moon and the sun, and then all 3 of them share that in the gravitational field between them. So notice we also, if we wanted to get the total potential energy, we would need the gravitational potential energy of the moon and the sun. Okay, and so what would that be? What would the equation look like if I wanted the moon and the sun? I would need a negative sign. I'll write that. I think I got the hard part there. Here we go. I know I need G, mass of the moon, mass of the sun. What do I need in the basement for this particular problem?
Difference of the radius.
The radii difference, yeah. So in this case, I need the center to center distance. It's always center to center distance. We're treating these like point particles. So would be what minus what in this case?
RES plus RE.
Yeah, exactly. So there you go. So far, so good? All right. Let's see, is there anything else here? Oh, we already talked about the tides. Okay, got it. So I'm confident that you could punch in numbers and add these all up. Are you starting to feel okay with the scientific notation, punching them in, getting that done? Ready to do some harder stuff? Let's take a look at this next one. Look at 13.2. I'm going to go over to the next board. Oops. Okay. See better.
So does gravity just affect translation or also rotation?
We could discuss, let's talk about that soon, but, yeah, it's both. How about I just say it that way? The planet, yeah, it's complicated. More on that in a minute. Is that cool? Yeah, yeah. I mean, the main thing that you think about is orbits, right? You could view an orbit of a point particle as translation, or you could view it as rotation, right? So, yeah, it depends on how you're viewing the problem and what you're choosing to think about. The spin of the planet as well affects the launch of things, right? So, yeah, all kinds of factors get in there. It's complicated. All right, 13.2, what was I doing? Sorry. It's slightly interesting, right? I hope you're having a little bit of fun here. Okay, so let's say we have a planet. So this is a large object. If that planet could be the Earth. This is where we see the prefixes sometimes make it a little bit easier to think. What was it, 24? Thank you. And now let's start with a small mass, a 1 kilogram mass. Ignore the sig figs. All right. Typically, when we're talking about a plane that's flying near the Earth, we don't describe the distance from the center to the plane. What measurement does a plane use when they're flying above the ground? Altitude. Altitude. So what we want to do is start using terms that normal human beings use instead of these obscure physics ones. So h would be the altitude above the planet's surface. Now here we're making an assumption that the planet is a perfectly smooth sphere, which is actually pretty good percentage-wise, but obviously what you describe as altitude would vary depending on whether you're above a mountain or a valley or things like that. But for now, let's assume it's a perfectly smooth sphere and altitude is just h. Okay, on the hundreds of kilometers scale, that's true. All right. So in this case, notice I could rewrite the force equation. And notice something. This is a common thing. I'm going to try and emphasize this. When you're writing this, a lot of times physics teachers will do a capital M for the big mass and a little m for the small mass. That way we don't have to use as many subscripts. So then the force would be G M M that would be the force magnitude. Okay? All right, let me see where I want to go with this one. Notice we could actually write this as force equals mg if g is equal to everything except for m. Can you guys do me a favor and punch in these numbers if we assume the altitude is 0? Just punch in G, capital M here, which is mass of the Earth, over the radius of the Earth squared. Just with h equals 0, what do we get? punch it in, verify. 6.67 EE11 times, what was it, 5.97 EE24? Div, 6370 kilometers, 6370 EE3, right? This is how you would write that, 6370 EE3 in your calculator. What did you get?
9.84.
Yeah. Now, to be fair, all semester long, I've been saying G is 9.8, and I've completely glossed over this fact. G in Santa Maria is actually about 9.79, right? And different places around the planet are different. The average of G over the entire Earth's surface is something like 9.806. So if you've been one of those people punching in 9.81 and didn't know why, that's the average of the planet to 3 sig figs. But to be clear, if you have to do a really precise measurement, if you need 3 sig figs on G, the local uranium deposits will affect the measurement. And another thing that happens is your altitude. Think, different places on the planet are slightly above sea level, right? And so your location, all these factors will factor into a value of G. So that's why I'm always just really lazy and just say, let's call it 9.8, or sometimes I'll round it to 10. Got it? All right. What's going to happen to G as you go upwards? It's going to decrease. Does it go to 0 instantly? No. When you go above the planet, are you weightless? Yeah, gravity exists in outer space. We've been talking about it for about an hour now, hour and 15 minutes. Just because you go up high doesn't mean gravity doesn't exist anymore. Maybe you saw that Red Bull guy that jumped out of a spaceship and got going hella fast with the air resistance set to 0, basically. So just because you're in outer space doesn't mean you're weightless. Weightless is a perception. If you're orbiting the planet, you're constantly falling towards the Earth's surface, and then you feel or perceive weightlessness. But obviously you're not weightless if you're in orbit around the planet. Weight is the force that causes you to orbit the planet. So weightlessness is a misnomer. It's a perception or a feeling. It's like when you're driving the car and you feel pushed towards the outside. You're not really pushed towards the outside. You're pushed towards the center of the turn by the door. And as a result, you perceive because you're pushing against the door. Yeah, whatever. Is that enough on that? You're not weightless in space. It's just a bunch of crap.
Microgravity, right?
What's that?
Like some people call it microgravity, right?
Yeah, so now if H gets hella huge, then the G is pretty darn small, and maybe the gravitational force is negligible compared to some other force on you. But yeah, so you can call that a microgravity environment. But so what I recommend, and I don't usually do this, but I think you should actually do 13.2 at home and make the frickin' plot and deal with the units. I know you don't want to. Nobody ever likes to do the plot questions. But what I have discovered, especially in this chapter, I learned about the subject, even though I'd been teaching it for 10 years, when I made the plots. And the stuff that I learned was how to make sure I don't screw up. So I do think that making this plot for 13.2 at home is worth doing. Got it? Just do me that one favor and make it, because you have to deal with the units and yeah. So far, so good? How about we take a break and then we come back and talk about orbits? Cool? All right, let's do it. Take that break.
little bit.
Let me see here.
It hurts my soul too.
Oh, yeah, it's not that bad. Oh, well, that's the thing is I know this stuff is not what you first. I just remember thinking when I was in grad school, gee, I wish I would have done more coding because the people that did all the coding got all the good jobs. That's really what it is, right? So yeah, anybody that was in grad school that was coding had a better experience in grad school than I did. So if you're interested in going to grad school, there's my plug for learning how to code. Got it, Jules? You've heard me say this many times. Let's just look at this here. Oh, and I wanted to change the sim speed. Just go to 1 speed. So what we have here is an object that's orbiting. Michael, can you see that online? Jules, is it show? Okay, it's good.
Yeah, I
Okay.
can see it.
Okay, gotcha. All right, so now notice this is not a circular orbit. In fact, it's not elliptical either. If I spin this sideways, right, the planet started at the origin. This is going way too slow. Let's try 3. Ooh, let's go 3.3. Oh, no, let's do 5.55. Come on. All right, there we go. So what's happening here is we could see this moon is orbiting the planet. And you could think of this as like the moon orbiting the Earth as the Earth is perhaps going around the sun, right? If we want to understand these complicated orbits, you would think, oh, this is so difficult. No, it's just force and momentum and time. Let's take a look at this code really quick. Boring, right? Boring. It's just drawing some stuff. Boring. We'll do this more tomorrow in lab. Now look what I'm talking about here. Notice I define the mass, and notice the Earth's mass is a lot. Now, okay, this is not, these are rocks, so they're not the Earth, but notice 8e10 is what? 10 to the 8th times bigger than this. So that's why we see one of the masses just trucking along, not being affected. It's because its mass is so much bigger. For the same amount of force, it has negligible change in its motion. Now notice I'm going to define momentum down here. That's just mass times v. Why am I doing that? Because it's a very physicsy thing to do. But do you agree that's basically like saying I've told you the velocity, in particular, rock 1.v would equal rock 1.p divided by rock 1.m. Did that make any sense? So if I wanted velocity, I could just specify it. But it turns out there are things called, let's not talk. Let's just get to the rock. Literally rock. Notice here, take a second to read that bit of code and make sure you're okay with that. In this case, rock 1, 2, 2, the initial position is rock 1, right? We're going from rock 1 to rock 2. That's why rock 2 is the final. It's final minus initial. That's the most common mistake. Does that kind of make sense? This is a bit of code that I don't want to explain right now. Look at how easy this is. The force is, take a second to read that. G, mass 1, mass 2, negative R1 to 2. That's a vector. And because I use the full vector, not the hat, I divide by the magnitude cubed, or the distance cubed. I could also do this, dot hat, and divide it by the magnitude squared. That should give the same result. But I don't want to do that, so I'm going to go back to this. So in the code, it doesn't look that outrageous. Now inside the loop, when we're looking at this thing, all you have to do is each time the rock moves, you recalculate the R vector, you recalculate the force, and then we use our impulse momentum stuff. Remember that impulse crap from chapter 9? Momentum is changed by force dt. So this is updating the momentum. And then we update the position. That's just distance equals rate times time. We got a plot here, and then you draw some pretty arrows, and that's it. There's some other little things. We'll discuss that later. Let's just run this thing. So when it's running around here, we could see this. So this is, it's a pretty simple code, 30 lines or so. You can make it shorter if you wanted. Notice what's happening here. If we scroll down, this is a plot, and I didn't label it, I'm a bad person, but it's showing the distance between the two of them. So notice in this case, the distance is oscillating up and down. It's getting close to the planet, then far away. So when I go up there, notice it's very far from the planet right now. And as we go downwards, it's going to get very close to the planet. All right, so you could talk about perigee and apogee if you're interested. So it turns out it's fairly straightforward to do real life models of these. But what we might do is first do a toy problem. Let's figure out the one special speed that makes this a circular orbit. Does that make sense? Right? Because this is an elliptical orbit. This is much more complicated. Let's try and analyze a circular orbit on paper, and we could use that to check this code tomorrow in class. Michael, you got all that? Or any questions while I got this up on Zoom? Or any from anyone else? Yes, question?
So use the formula when the R1 to 2 is like to the third power.
Yes, yes. So from a practical standpoint, in the code, we usually use this one, the cubed, right? The vector over R cubed rather than the hat vector over R squared. It's just easier to code.
Oh, it's just,
That's it. Got it?
so it doesn't really matter.
It doesn't matter at all. And generally speaking, most students are bad at hat vectors and a little better at just full R vectors, right? Because to get the hat vector, you first have to get the full vector, then divide by the magnitude. Well, this is just, that's just one less algebra mistake you might make. You see what I'm saying? It's not that they're any different. It's just a little bit less math. That's one less spot to screw up. That's it. All right. Good question. Others? All right. All right. Let's go to, I'm going to try and use blank. Blank. Roll this up and look at the orbit question. I believe it's 13.3. And Edgar, you had asked about this code, so later on you could go back and watch this video and hit pause to kind of learn about the code if you need it later, right? Anybody that wants to. Okay. Let's see. Okay. Now let me get on the right monitor. Go. Let's do a circular orbit. We're going to try and analyze a circular orbit problem. This is a classic. Make sure you put a star next to this one. You got to basically, this is one of the ones that's potentially a final exam type question. I might do some variation on it. All right. So we have this point particle here. We've got this planet here. So some shading might be nice here. I'm going to call this capital M, the big planet. I'm going to call this lowercase n. This is moving with some speed v. Our assumptions are that the mass of the planet is much, much bigger than the mass of the satellite. That way we can ignore the motion of the planet and just assume it's fixed in place. Okay. All right. Part A. I want the potential energy. I want the potential energy. Would I say potential energy of the satellite? Or is that wrong? I don't want the potential energy of the satellite. I want the potential energy of the system, the two-mass system. Okay, remember, the satellite will be the one that's most affected by the changes, but that doesn't mean it's not shared. What's the equation for U? negative G. I need the two masses. What do I divide by? Is it R or R squared? Now, what is R in this case? The center to center distance. So let me just kind of,
R plus H.
yeah. That's the radius I need to use. So in this case, I need to do that. So that's the answer for part A. How about part B? I want the speed of the satellite. Huh. It's in a circular orbit. What should we do? Circular motion, force, FBD. Okay, so here it is. Give me one force on the mass, little m. Gravity. We used to say mg, but now it's going to be g m n divided by what?
R squared.
In this case, little r squared is. So whenever you have to deal with altitude, basically you just change little r to big R plus H. Okay. What's the other force? Oh, go ahead.
So how there's a square root in that one and not in
The squared. It's a squared, not square root.
the square root?
Yeah, I know what you mean. Remember, this is, I guess, I'm trying to kind of find a better way than just saying it's just the way it is. But for right now, I just want to say it's just the way it is. This one has to the first power and this one has to the second, right? And so this has to do with the fact that as you get farther away from the mass, we could talk about the field and we could talk about energy and the surface area of a sphere being 4 pi r squared and to make the energy density be constant, blah, blah, blah. Something about that. Basically, we end up having a 1 over r squared for the force. And then remember, potential energy was derived from that by doing that integral. And that's why we get this r to the negative 1, because when you integrate r to the negative 2, we get that r to the negative 1. All right, I know that's weird, but that's just the way it is. This is a force, not the energy. So to be clear, this is the force due to universal gravitation. Sometimes we write force big G. Cool. Where this is U due to universal gravitation. So we might call that U big G. What's the other force on this thing as it's orbiting? Nothing. I was trying to trick you. You didn't fall for it. Damn you. Right? If this thing's really in orbit, we'd hopefully be above the atmosphere enough that there's a negligible drag force. All right, anyways, let's do that. So what is this equal to then? G M M over R plus H, quantity squared, is equal to, that's the force. The speed is constant, right? That's what the premise is. So is this thing accelerating?
No.
Yes. Constant speed in a circle is AC. Gotcha. Right. Okay. So which mass do I use? Is it big M or little m? Little m. Why?
Because big M is not affected.
We're talking about the forces on little m, so it's little ma. You could do the same math on big M. But because big M is so huge, AC would be, got it? So it's whichever mass you drew an FBD for goes right here. What distance do I use? What's the radius of the circular motion? It's AC is V squared over R, right? Is it capital R or little r in this picture? It's the radius of the circular motion.
Oh, so the altitude.
It's not H.
R plus H.
R plus H. Do you agree the circular motion has radius R, capital R plus H? All right? So conveniently, because this mass is enormous, the center distance and the radius of the circle are the same. That is not true for the Earth and the Moon. Okay, we could discuss that more in a later problem. Turns out the center of mass for the Earth-Moon system is what? I think 2/3 of the way out or 1/3, I forget. All right, whatever. We're trying to find V. What drops out here? What drops out? Little m
And one of the RH.
and one of the RH. All right, so what's V? There we go. Side note, set this speed to the speed of light, and you've got yourself the condition for a black hole. Right? We'll talk about more of that. We'll do that in a little bit. More on that later. It's not exactly the same, but it's a different problem. So if you're into black hole physics, that's coming soon. I'm gonna leave it at that. All right. What's part C? What's the kinetic energy of the satellite? This is kind of where you were going. We can treat this as a point particle. What's the kinetic energy for this point particle moving with speed v? 1/2 mv squared. But isn't it a point particle that's rotating? It's also 1/2 I omega squared, where I is m. Either one of these would work. But the idea is you don't want to do both of them, because you could either view it as rotating, and then you would use I omega, but the moment of inertia is this. But notice that's exactly the same as just plain old 1/2 mv squared. Either way, is that okay? You either view it as rotating or as translating around. Now I'm going to pick the easier one. That one. So what's the kinetic energy? Just take a second to do this. When I square that, what's GM? What's that?
You were skipping ahead.
Yeah, that's right. Nope. It's not half of the force.
Half of the potential.
It's not half of the potential energy.
Awesome.
It's half of negative the potential energy. Do you agree? It's half of negative U. Negative 1/2 UG. Good identification. That's what I was going to see if somebody noticed. It's the opposite of half of the gravitational potential energy. So what, I think part D, let me make sure I'm not skipping ahead. D, what is the total energy of this particle as it's orbiting? Do you agree that would just be K plus U? Just add the two energies together? Notice it would be negative 1/2 G M M over capital R plus the altitude. Right? Because this is going to take away half of that. Notice the total energy is negative. If you did chemistry, perhaps you know the energy of the hydrogen atom in its ground state is negative 13.6 eV. Anybody know that? Never mind that. Here's the deal. This is a special thing. Maybe you're tired, but check this out. If you are trapped in an orbit whether it's elliptical or circular, the total energy of a trapped body is negative, right? If you're trapped in an orbit around something else, your total energy is usually considered to be negative. And what we say is, if you want to escape, you would have to add energy to the satellite, like maybe burn some fuel and speed up. And then you could escape the orbit by getting to zero energy. Got that? Isn't that weird? So, and notice, the closer you get to the planet, what happens to H? It goes, yeah, it gets smaller. So what happens to your energy as you get closer to the planet? It gets what?
Bigger.
I would say it gets more negative. And the reason do you agree?
Yeah.
This becomes a bigger number, but it's a negative. So depending on who you're talking to, a larger negative number, they might say, well, that's a small, right? So I think it's better, yes, the magnitude of the energy, but then energy is a scalar, so we don't. This is the wording I would like you to use. When we're talking about energy, I would say more positive or more negative. And that gets you out of a jam a lot of times. And that makes it very clear what you're saying. You either say the energy becomes more positive or more negative. And remember, if the energy becomes more negative, that makes sense. We're going downhill, right? We're getting closer to the planet. We're getting lower elevation. All right. If you go uphill, your total energy becomes less negative. That's like gaining potential, right? So, okay. All right. What else? What else here? Oh, look at part E. If you go to a higher orbit, what happens to your energy? I just did it the other way. So if we go to a higher orbit, H gets bigger, this term gets smaller, it becomes less negative. So that's what I want you to say. As H goes up, total erg less negative, or you could say more positive. Obviously, it's not really positive, but -1 is more positive than -2 in my book. So this is probably the better phrasing of time. Say it that way. Determine period of the orbit. How could we get period? Which of these would help us figure out the period? Which part? A, B, C, D, or E? I want the period. Where's the period hidden? In the V, right? In particular, what does period mean? Time to do what? To orbit once, or one revolution, right? Time for one rev. Okay, so if this is a constant V, how does V relate to the period? Think about the units. What are the units of V? Meters per second. How many meters? Give me an equation for the meters. What's this? Who is the roundest knight at King Arthur's table? Circumference is 2 pi, which R? Little r or big R?
R plus H.
Yes, big R plus H or little r. Okay. That's the meters. What's the time to go around once? What do we call that? The period. Meters per second equals meters per second. If you needed to get the period, you could rearrange this. Let's do that really quick. Solve for the period. I know I'm working backwards here. What was this, part F? Sheesh. Solve that for period. So this goes over here, this comes over here and flips upside down. Okay. notice we could clean this up. It's some constant times r plus 8. I'm just going to write that as green r times r to the 3/2. Right? Because there's 2/2 and another 1/2. And remember, little r here is big R plus h. All right, it's so sloppy. I didn't eat this. That's Kepler's third law. Or is it second? I forget. Third. Got it? Cool? The period of the orbit. This begs the question to me. Let's say I wanted to spy on my students 24 hours a day by putting a satellite with a high resolution camera and have it just stay above a certain spot on the Earth, right? What would the period of that satellite need to be if I wanted to hover above the same spot on the Earth? Imagine this planet's rotating. How long does it take our planet to rotate? One time. 24 hours. What if we set the period to 24 hours? If we do that, the satellite would be geosynchronous. It would be in the same spot all the time, and we could spy on students and make sure they're doing only physics, never math. Just kidding, I love math.
Or chemistry.
What's that?
Or chemistry.
Yeah, no chemistry. That would be automatic failure. What is going on here? Why is this doing this to me? Yeah, it just turned on by itself. You guys saw that, right? Okay. Just chalk it up to the weirdest semester on the planet. Everything
Well, isn't omega different on the?
at different latitudes.
Yeah.
Yeah. Yeah, so we're doing a simple case of geosynchronous above the equator at this point. Yeah. Good?
Yeah.
Now, to be fair, right, you could probably put a satellite right here, right? Okay, so let's say we're viewing the Earth from the top, okay? And so this is the North Pole. You cool with that? And so, right, now keep in mind, you could have some resolution going at an angle as well. But so even if you're up here, right, we probably have to think more carefully about having satellites if we're at different latitudes, because then we might want to have different orbits and things like this. And so maybe we'd use a mesh, but let's not go that way. That's not our goal right now. Is that good enough?
Yeah.
But if we're just talking about one satellite around the equator, this would work. Good. Cool? Well, at this point, you could plug in the period and see what the altitude needs to be. I think I did that somewhere. Oh, okay, whatever. Yeah. So if you want to, I thought I did that somewhere. Where is that one? Give me just a sec. All right. I think that's enough on that one. So I have a question for you here. Look at 13.3 and a half. A satellite orbits the Earth. The Earth's gravity is certainly weaker up here, right? So this is a related question. Okay. And as an example, I put in the numbers. I put in 400 kilometers in the equation from 13.2, and I found that at 400 kilometers above the Earth's surface, that's pretty big. G is still 8.7 meters per second squared, even up there at 400 kilometers. For reference, I punched in the numbers and found a speed. So at that altitude, so if H is 400 kilometers and you do all the prefixes and numbers right, the speed required for a circular orbit is 7.7 kilometers per second. How should you respond to the question, what keeps the satellite up there? What keeps the satellite up there? That's what, right? Could you imagine some kid coming up to you and asking that? I get asked that. What keeps the satellite up there? What do you think? I wouldn't say anything keeps it up there. It's always falling. It just never hits. That's it, right? Because centripetal acceleration is not a force. That doesn't keep it up there. It has centripetal acceleration. I agree with that. You could argue that the centripetal acceleration could be viewed as a fictitious force, but that doesn't exist. It's fictitious. Nothing keeps it up there. It just never hits. It's a subtle change in how I view that. But yeah, go ahead.
So was it like moving fast enough to like not hit the ground?
Yeah, if you throw it fast enough, right, it's falling. Like, look at this right here. It fell down. But it was moving so fast that by the time it fell down, the distance was still the same. Then it falls down again. There's a classic picture they show in some textbooks. I'm just going to draw this one. So my answer to that 13.3 is nothing keeps it up there. It's just moving so quickly it never hits. I know this is going to seem crazy, but let's say you have a planet. And then at the top of the planet, there's a giant mountain. And on top of this mountain, there's a really good baseball player or something. Okay. And this baseball player can whip that baseball. First, they start out, they throw it kind of slow and it goes like this, right? Already that's pretty insane if you think about that. That would be several 1,000-mile throw or something, right? They throw it a little bit faster. It hits right here, right? So it's falling towards the earth. If they throw it even faster, it's going to hit right there. If they go at just the right speed and they're on a planet with no air resistance, it goes all the way around and hits them in the back of the head. It's falling the whole time. It just never hits the planet. So in an orbit, I want you to think about it as constantly falling. Got it? Now think about this. If you've ever heard of the vomit comet, where you're going up and down, the reason you feel weightless is because the plane is flying in the same parabolic trajectory as free fall. And so you're just falling inside the plane without air resistance. So you feel weightless, but you're not. Okay, is that good? All right. All right. So now I feel like we're ready to get to some test level type questions. That was one of them. You can imagine me do a variation on this. Let me go back to the main screen for the Zoom. You could imagine me asking you some question. What if I put in particular numbers and had you solve for something, right? And deal with the numbers in this type of problem. Or what if I made this a little bit annoying, right? Where, like I said, oh, the radius of the planet is R and the height is 6R. So that you had to like go through and do it all with one particular set so that the radius ends up being, so it's just a little bit of messy algebra. Got it? You could do all that. What if I said this mass is equal to 100 times that mass so that you could have some stuff drop out, right? So I could imagine doing some problem like this where I change the parameters a little bit and see if you could rederive something that we just did. Got it? Put a check mark on that. Do that problem again at home without looking at the notes. And if you get stuck, look at the video. All right. Now let's look at another variation that's like an exam question here. 13.5. We're finally ready to start doing some angles. Okay. Three at the origin. I don't know if I'm using the same colors as the workbook. I should have checked. I have one up here. Over here. I have two. We know that the masses are 1, 2, and 3. Just to keep it easy. Mass 1. You know what? I might change this one to red. Sorry about that. I think that shows up a little better. Got 30 centimeters, 1 to 3. Okay, so this (40 centimeters), and this 30.0 centimeters, right? Ah, shit. I read the question now. It says in the solutions I used green for 1 on 3. Crap. All right, just to make this match, I'm going to change this one to green. And red for the other one. Okay, so this is the one. Sorry about that, but might as well make it match if we can. Sorry. Red and green are a horrible choice, but sorry. Should change that to blue. Okay. Part A says, go with your gut. Which one of these masses is going to exert more force on 3? What's your gut? You've got 1 and 2. 2's a little bit bigger. Well, it's twice as big, but it's a little bit farther away. Who do you think is going to exert more force, 1 or 2 on object 3? What's your gut tell you?
2.
2, and what's your reasoning?
Oh,
It's farther away. Which factor should matter more, the mass or the distance? What did you say? Which matters more? Why does the distance matter more for the force? Because it's squared. So this is tough. Do you agree that 2 is twice as big? The distance isn't twice as much. What's the distance between them? What's this distance on this side? Tell me right now. What's this distance? You know this. It's the hypotenuse. 50. Yeah, that's funny. So it's not twice the distance. I don't know. So how about I say it this way? Do you agree they're probably about the same? All right. Recognize this problem, Jules? It's like the first question in physics 163, except we do it with charge, and I do the same stupid shtick. All right. So what direction is the force on 3 due to mass 1? Which way does mass 1 exert a force on 3? Up, on 3. Where do I draw it? Up here? No, it's on 3. That's the force of 1 on 3. Do you agree that 3 exerts a similar sized force on 1, but I don't care about it right now. I'm worried about on 3. Okay, what's the direction of the force of 2 on 3?
Depends on if we're talking Cartesian or polar.
Well, just show me with your finger. Yeah, that way. Got it. Now, I don't know which one's bigger. Whoops, not 1 on 3. Yeah. And you brought up a good point. We could do this in polar form or Cartesian form. So knowing me, which way do you think I'm going to do? Both. Just to show you both ways. And at this point, you've got the solutions. Do you guys want to just look at it and do it? Or do you want me to do it up on the board with you? How about I do it with you, just so, right? All right, let's do it. Let's do it. But if you want to, you could use a computer at the edge and just do it at your own pace if I'm too slow. Okay. I cannot stress this enough. Here's the deal you've got to know for a test question on this type. Drives me nuts. Force net on 3 is a vector. You cannot just add the magnitudes. Okay? I need to do the vectors. Every year, it happens where people forget this one step of including the vector because they're in a hurry. Understandable. You've got to do the vectors to get the answer right. If you just add these magnitudes, you're never going to get it. So now we could get force. Do you agree force 1 on 3 is pretty easy? Do you agree force 1 on 3? You could just get the magnitude and then slap a J hat on it, right? So let's do that. This one I calculated using the magnitude and the direction because I just knew the answer. And I don't want to overthink and have to do R hat crap if I don't need to. Does that make sense? Now we can do force 2 on 3 in 2 ways. I could say it's G mass 2 mass 3 divided by the distance. See the advantage of the subscripts now? That's basically what I was telling you earlier. And then I could try and get the direction. And like you were saying, there's some Cartesian. So there's going to be some in the I hat and then some in the J hat. And in fact, do you agree there's some in the negative I hat? Because it goes to the left. We need an angle of some kind, right? SOHCAHTOA. So in this case, let's call this angle theta. What's this angle? That's also theta. Now notice, what's cosine of theta? What's sine of theta? Just pick one. Let's do cosine of theta. Use this triangle.
Cosine theta equals 30 over 50.
Yeah, and the units drop out, so then I don't have to worry about those centimeters screwing me up. I'd have to worry about the centimeters in here. Do you agree? But so, do you agree this is 30 over 50? And the centimeters drop. So it's 0.6. Don't worry about getting the angle. I've got cosine of the angle. What's sine of the angle going to be? 40. That's 0.8. And now I look. Does the x component, let me wait for a sec. I want to get your eyes on this. I want to do this together. Tell me when you're ready. I'll wait. Okay. Let's take a look here. Do you agree this one has some component this way? Is that going to be sine or cosine of theta? That's going to need a cosine. So I'll just slap in at 0.6. And I've already got the minus sign right there to account for to the left. So I have to put in the cosine and then I put in the minus I hat. What's the j hat term going to be? And we could keep extra sig figs, but I'm really lazy. Cool? That's one way to do it.
Angles times the magnitude.
What's that?
Angles times the magnitude.
Sines and cosines of the angles. Yeah. But I know what you mean. Some sort of angular part with the hats. Yeah. And so G, I wonder what minus R hat is. This is just a fancy way of. Now check this out. You could do all that. And this works great. But I'm going to write this another way. Give me a second. I'll get out of the way. It's going to be G M M over R cubed minus R vector. Now, when I do this, what is negative R to, well, let's just get R 2 to 3 before we worry about the minus sign. What's R 2 to 3? I want to go from 2 to 3. Give it to me in Cartesian form. How much in the X? As I go from 2 to 3.
30.
30 I hat positive. How much in the J hat?
Negative 40.
Now, I haven't shown you this, but look, there's this minus sign right here. That's going to flip the signs. There's an extra magnitude of R, which is the extra 50 centimeters right there. Do you agree that's going to give me the exact same result? Take a second to look at it. This one has R squared. If you take one of these R, that moves it over here. That's going to divide this by 50 centimeters. The sign, which comes from the definition, flips it. We get exactly the same results. Just want to emphasize that minus sign there. Okay. Cool? Now, which way is more general? This way. Which way works in 3D just as easily? That's, I guess, why I don't use the blank sometimes, huh? Got it? So this method is also exactly the same as how you code it. So to be fair, your test level question is not going to be 3D. So if you like doing it with SOHCAHTOA, you can do it with SOHCAHTOA. But the next class, you kind of have to get better at this. Got it? So depending on what your schedule is like and what you're good at, doing this style of just doing SOHCAHTOA is going to work for this class. But this is the better way. In general, this is how we're going to code it tomorrow. Maybe you'll get used to it. Cool? Was there a question? Yes.
I would, it's also just saying like F2 on 3x and F2 on.
Yes. So you could just say, you could split this thing up. What he's saying is absolutely. You're just saying, look, this is F23x. This is F23y. And then you just do SOHCAHTOA on this thing, right? So you say, this is the magnitude, and then you SOHCAHTOA it. Cool? So now I took a lot of time writing up this particular solution. So put a star next to this one and try and do it again at home. And make sure you plug in the numbers. In particular, what are the things that we got to watch out for in this type of problem? Minus signs, angles, and units. Centimeters are not meters. What do you think I'm going to do to you on testing? You know I'm not going to give you normal units to see if you remember to convert, right? In the real world, life is messy. You got to convert your units and get that. So I'm going to test you on that. All right. Yep.
So will we have to label our axes for this?
So in this case, you're right. You're basically calling me out, and rightly so. I'm assuming this is the X direction and this is the Y direction. Thank you for pointing that out. That's my default unless I specify otherwise. We normally assume this is X and that's Y. And I think if you look at the homework, generally speaking, I try to specify that sometimes, but looks like I forgot on this one. Cool? All right. So the rest of the page, in theory, you could do all those at this point. 13.6, 13.7, and 13.8. For fun, just to foreshadow the next class, look at the top of page 120. It's one of my favorite problems. 13.9, escape from planet of the physicists. Everything works on this planet, but only to within 10%. Everything is always a sphere. Social interaction is more awkward than it should be. Anyways, yeah, we're gonna talk about that next time. And notice this problem is also fun because it mentions AK-47s. So it's like, it's a weird problem. We're gonna pick up next time there. If you are curious, this is something I mentioned earlier. I want to point this out. Look at problem 13.12 because it's almost time to go. We don't have time to do another problem. Remember how I was said people get confused why MGH is equal to negative GMM over R plus H? If you are passionate about understanding that relationship, 13.12 is for you. I go through that. I show you how to do the expansions. And I tell you about why you might care. So if you're a physicist, you should do 13.12, right? To learn, okay? And if you're not a physicist, maybe you could skip that one, okay? That's all I'm gonna say. And if you want me to go through it, I'll do it in office hours with you. If you wanted to know how the potential energy was derived, we still got 1 minute. Look at 13.11. There's where I actually do the full derivation of U equals negative GMM over R. So if you are a physicist, you should do 13.11 and 13.12. Got it? And you will learn a lot from that. And I can help you after class. Jules, is there anything you would like to say in the last minute here about any of this crap? You're good? Trying to quit? Okay. All right. Questions?
For problem 13.9, is the muzzle velocity for the AK-47, is that accurate or did you just make that up?
I believe I looked it up. Yeah. So we'll go into that. Yeah, and we'll talk more about that later. So yeah, you tell me, look it up.
Okay.
And we can Google it right now, but I believe I actually looked it up.
How much better are the toasters in there?
Well, we'll just have to find out. We'll have to go there and then try and escape. Yeah. All right. By the way, the last thing, on a lot of these problems, you're going to see something about CubeSats. Has anybody ever heard of a CubeSat? I know that some of you might be interested in going to Cal Poly. Turns out CubeSats were invented at Stanford and Cal Poly. They have a lab where students can control them.
Isn't it like the little cube satellites that you can make that fit together kind of like Legos that they use for the DART shuttle?
That I'm not sure, but yeah, they're basically
I think it was like
small.
the camera that they had was a CubeSat.
Yeah, they're basically 1 kilogram satellites that you can launch up. And if you're really into that, you can actually get a job at Cal Poly, a student worker job, working on the controls of it. So that's kind of cool. Yeah, but you're right. And anyways, that's kind of a cool hip thing in the world of satellites these days. Nice job, Robert. All right, I'm gonna turn this hell off.